All right, so let's get started. Sanjoy Dasgupta needs no introduction. So he's, of course, our fearless leader for this program. From UCSD, has done all sorts of pioneering work, including in the area of active learning, and that's one of the topics of the tutorial this afternoon. Welcome, Sanjoy.
Okay, thank you. Rob, Nowak, and I are going to be talking about interactive learning, and so I'll do the first half, and Rob will do the second half. So the first question is, what is this interactive learning thing? And it's most easily thought of in contrast with the way supervised learning usually happens, which is that a data set is obtained in some way, a human being is brought in to label all of these data points painstakingly. The human being goes away, and at some later point in time, a machine is started up, given this labeled data set and told to find a classifier. Okay, so there's no interaction at all between the human and the learning machine. Okay, so interactive learning refers to various scenarios, including those in which the learning machine interacts or engages adaptively with a human while learning is taking place. So it's like the human and the machine are kind of puzzling over the data set together. Okay? And sometimes it's actually not a human being. So for example, the machine might be interacting with a robot that is conducting biological experiments. Or the machine might be doing experiments on a network, like measuring latencies or stuff like that. Okay? So this is a vague definition of interactive learning. The learning machine engages adaptively with an information source during learning. It would be nice to have a more formal definition, okay? But I don't think we have one. And in the absence of one, I'll just go over a few sort of examples just to illustrate the range of interactive learning that takes place. Okay, so one type of interactive learning that has really been studied a lot, perhaps the most, is what's usually just called active learning. Okay, and the situation here is that you have a very large unlabeled data set, okay, maybe 100,000 documents or something, and it's simply infeasible to have a human label all of these. Okay, it's too expensive, it's too time consuming. Maybe you can label 1,000 of them. Okay, which 1,000 do you pick? And in active learning, this is done in an adaptive way. Okay, the machine might pick a few randomly, and then after a while say, okay, you know what? This is the one I want next. That is the one that's going to give me the most information, and this is the one I want next, and so on. Okay, and so it adaptively picks a few examples, and the sort of questions that we have in this case are: what sort of strategy should the machine follow, and what is the trade-off we get between the number of labels queried and the error of the classifier? Is this way better than random querying? And as so this is something we'll talk about quite a lot, and as we'll see, it is way better. Okay, and so this is what we would usually call active learning. Another kind of interaction, which has been studied much less in theory, almost none at all, would be called explanation-based learning. And here what happens is that the human labels a data point, but also provides an explanation for it, okay, often in the form of features. And so let me give you an example. Okay, so let's say the human is given a document to label. So the human reads through the document and says, oh, okay, after quickly skimming it, the human says, okay, this is obviously a sports document. But now if the labeler has gone to the trouble of actually, skimming the document, it's almost no additional effort to also maybe highlight a few words that are highly predictive of that label, like cricket or batsman or umpire or something like that. Okay, and so this is very little extra effort, and it could make a huge difference in terms of for example, feature selection in a high-dimensional space. Another example that that has been tried out quite a lot in computer vision is systems where, for example, a new picture of a bird comes up. The computer looks at it and says, oh, this yellow bird, I think it's a canary, okay? And then asks the human, am I right? And so the human, who's a bird expert, looks at it and says, no, that's not, that is something else, maybe a yellow warbler or something. And then, in addition to that label, also clicks on a part of the image that explains the difference. For example, the beak. Clicks on the beak. Okay, and that's a discriminative feature. Okay, so this sort of explanation-based learning has really not been studied a lot formally, sort of in a mathematical sense, but it's very interesting. And so sort of the questions are, what is the benefit that these additional explanations provide beyond labels alone? Okay. And secondly, in many of these situations, there's inherent ambiguity in the feedback. So the human is clicking on the beak, and what does that mean? Like, what is the feature? Is it the color of the beak? Is it the shape of the beak? Is it the fact that there's a beak? Is it the whole head, actually? What is the, there's a lot of ambiguity in this feedback, and it's kind of interesting to figure out how to deal with that. Another kind of interaction, which I think would be extremely useful to have a lot more of, is interaction for unsupervised learning. Okay, so over the past decade or two, there's been some really amazing progress in algorithms for unsupervised learning. Okay, so we have methods now that will find, the generating mixture of Gaussians, or the right topic model, or the optimal k-mean solution, or whatever. And this is fantastic. But at the end of the day, okay, so you now have the optimal k-mean solution, but it's still not the clustering you actually want. Okay, and the reason for that is that when you have a high-dimensional data set, there are just so many different ways you can slice or dice it. If you're like clustering, say, participants of the Simons program, would it be according to geographic location, or academic trajectory, or areas of interest? I mean, these are all very natural ways to cluster the data. They all correspond to salient clusters of people. They're all perfectly legitimate. And there's no way that an unsupervised algorithm can magically know which of these alternatives is the one that you actually want. Okay, and so this is an area that seems ripe for interaction. Okay, so how would that take place in the matter of clustering? Well, so let's say that the machine has generated some clustering of, say, 100,000 points. How could it get feedback from the user? Well, you can't show the user all 100,000 points and say, oh, do you like this clustering? So, one example of the sort of things people have tried is to say, okay, well, I can't show you my full clustering, but I'm going to show you a little random snapshot of it. Here's what the clustering looks like, limited to just 6 points. What do you think about this? And then the human says, oh, it doesn't look quite right. I don't know exactly how to pinpoint what's wrong with it, but one thing I can definitely tell you is that dolphin and whale have to be together, something like that. So you get this sort of simple feedback, a simple constraint of that form. Or if it's a hierarchical clustering, the human again says, okay, you've shown me the restriction of the hierarchy to just these 6 points. I can't tell you the correct hierarchy even for those 6 points, because that's too difficult for my brain. But what I can definitely tell you is that dolphin and whale should be merged before zebra is added in, or something like that. Okay? And so the question is, what are interactive schemes of this form for the popular kinds of unsupervised learning? And and how rapidly can you converge to the right target, the one that you actually want? Okay. So some of the questions that arise in these settings is, first of all, of course, what are efficient ways to do interaction? What is the minimum amount of interaction needed to get to arrive at a structure that is adequate for the human? In many situations, it's interesting to ask whether interaction is actually helping to overcome computational barriers. Okay, is the problem NP hard without interaction, and actually easy with interaction? Then there are questions about the modes of interaction. What sort of questions can you ask that are easy for a human to answer and that lead to reliable feedback? And so this might seem like it's purely a human-computer interface kind of question, but I think it's also amenable to theory. I mean, maybe not mathematical theory, but theory in the form of identifying underlying principles and reasoning based on those. And then, one of the things that really I find most exciting about this area is the communication gap between the human and the machine in these sorts of interactive scenarios. Okay, nobody knows what representation the human has. we all know what representation the machine has, but we don't understand it. What do the nodes in the neural net mean? How can, so labels are safe, everybody agrees on what a label means, but the minute you move to richer interaction, there is this communication gap that has to be bridged. And what are ways of bridging it, and what can you show about it? So these are some of the questions that arise in interactive learning. And what I'll be talking about today is mostly the stuff that's known, which is not that much, having to do with the active learning of classifiers. And then Rob will be talking about richer classes of structures and also about issues that arise in practice. Okay. So active learning, okay. So this is a problem of considerable practical importance, and so there are actually lots of heuristics for doing active learning, and I can, and the way a lot of them work is as follows. So you have this huge data set, you have to adaptively decide which points that you're going to query, okay? So the typical way this goes is you start by picking a few points at random, okay? Then, just to get the lay of the land, okay, and then maybe you fit a classifier to those. And then once you've done that, then you begin the actual intelligent querying loop, where you say, well, you know what? I don't need to ask for the label of this because that's probably a red, okay? Let me focus on the points close to the boundary, okay? And so you say, okay, let me ask for that one, and then you get a few more labels, and then you refit the classifier, and then you keep going in this way. So it's very intuitive. Makes sense. You ask for the labels of things that you are most uncertain about, and it seems, therefore, in some sort of information theoretic sense that, you are maximizing the amount of information you get from each label. Okay. So these are very intuitive heuristics. And so, as theoreticians, the question before us, okay, how do we analyze these things? These certainly make sense. They seem sensible. How do we analyze them? And sort of the default model for doing this would probably be the statistical learning theory model, okay? Which says that there is some unknown underlying distribution from which all data points are generated. Okay, so it's a joint distribution on data and labels. We don't know what it is, but everything comes from this distribution. We are picking a classifier from some class H, okay, and we want to find the very best thing in the class, the thing that has lowest error on that underlying distribution. Now, since we don't know what the distribution is, we just take a few samples from it, and then we do well on those samples, and then the statistical theory takes over and tells us that as the number of samples goes to infinity, we converge to that best possible classifier. Okay, so that's the statistical learning model. So now with this sort of framework in mind, we can go back to those heuristics and say, okay, well, let's see how we would think about this in the model of statistical learning theory. So you have this vast body of unlabeled points. You pick a few of them at random to label, okay? That's great. The random samples you have are genuinely random draws from the underlying distribution. That's good. Now you begin your active learning loop, okay? So now you're querying points near the boundary, and as time goes on, you get more and more points that are kind of piled up near where you think the boundary is. Do those look like the underlying distribution? Okay, and this is when you start to run into some trouble. Okay, all of a sudden this doesn't seem like it's necessarily such a great idea. As time goes on, you are getting a set of label points that looks less and less like this underlying distribution P. Does it really make sense to optimize with respect to this label set? Are these heuristics such a great idea after all? Okay, so there seems to be some sort of bias sampling that's going on. Okay, and so so let's look at a concrete example of the problems that this might cause. Okay, so here's a very simple scenario where the data lies on a line. So all the data is one-dimensional. Okay. And the sort of classifier we're looking for is just a threshold. And we're going to say green on this side, red on that side. We're just looking for a very simple type of classifier. Now the data is clustered. There's like a cluster of red points over here, a big cluster of green points over here, and so on. So now you run your active learning heuristic. So you pick a few points at random.
Question? What's the 5%? So what's a 5% doing on the left?
Yeah, so this is a 5% green. These are 5% of points of which half are red and half are green.
Wait, so but your class, red means?
The two labels are red and green.
But you said the label is based on a threshold, so
yeah, so right. So the classifier we're looking for is, there's nothing that has zero error.
Oh, it's not.
Right? Okay, so yeah. So, so now, so let's see what happens. So you pick a few points at random. They'll probably be from these extremal clusters, since that's where most of the data lies. So you get a few reds, a few greens. And so your initial boundary will be somewhere in the middle over here. Now, based on that, the points you're going to query are going to be points from the middle. All the points that you see will reinforce your belief that this is the boundary you're looking for. And so this is the boundary you're going to converge to. But it's a boundary that has 5% error. Whereas if you put the boundary over here, you would just have 2.5% error. Okay? So forget about using labels efficiently. In this situation, even if you had infinitely many labels, you would converge to the wrong thing. Okay? So, so these methods lack statistical consistency, which is like a very basic thing that we hope for from learning methods. Yeah?
Can you have this problem if the optimal solution is 0 error?
Yeah, so then it will go away. Right? So this is in the more general separable case, right? Okay, so so one of the basic challenges in active learning is dealing with bias sampling. You're creating a bias sample. How do you manage this in such a way that you can at least guarantee consistency? You know, and that's a very basic requirement. And after that, you can worry about optimizing the number of labels. Yeah.
So I don't think you can get around this, because if you look at the hardness results, I think some queries won't tell you anything. Like they're PCB based, so you basically have to query a lot to get any idea.
Well,
So I'm just saying this is inherent.
Put on a line.
Oh, I don't know about the line, but for linear.
No, I mean, linear in one dimension, you can do with 1 over epsilon samples without active
Not
and
one
everything's
dimensional,
fine.
high dimensional linear.
we'll see plenty of positive results. Huh?
Sorry?
We'll see plenty of positive results pretty soon.
But this problem will remain, I think.
Right, so the problem of finding, say, the best hyperplane, right, is of course NP hard.
Yeah.
But,
even with, if it's not.
Yeah, but this is sort of an orthogonal problem that can be solved, which is
This
just.
can be solved? So I'm actually suggesting it's hard, but okay.
Well, we'll see. We'll see in a little bit. Okay. So one interesting question over here is there a generic fix to these heuristics that just makes them consistent? Okay. So forget about efficient use of labels. All these uncertainty-based heuristics, is there some generic thing you can do to them? Maybe it's a little bit of random sampling or something that just automatically makes them consistent. I don't know. That would be really nice. Yeah.
Isn't this the same kind of like exploration versus exploitation issue that comes up so often in all sorts of different areas?
Yeah, so this is an exploration versus exploitation issue in the sense that in this case, you don't see any points from this cluster. And yet, from the get-go, you're confident that everything here is red. Okay, so and so this is misplaced confidence. And so with better, with better confidence bounds, you would be able to avoid this with a little bit of exploration, which would require a little bit of exploration. Okay. So, so just adopting the statistical learning framework already gave us some insight into these heuristics. And the next form of insight that the model brings is just to try and understand what kind of benefits do we expect from active learning. Okay, so it's clearly non-trivial, even to get consistency. But what kind of benefits do we expect over random sampling? Okay, and the canonical example for that is, again, points on the line. Okay, so let's say now that we are actually in the separable case, and that what we are looking for is a threshold on the line, and everything to the right is going to be plus, everything to the left is going to be minus. Okay, so we're just looking for one number, and we know from generalization theory that if you want error epsilon, you need about 1 over epsilon labeled points. Because if you have 1 over epsilon points, then the distance between consecutive points is the probability mass between consecutive points is about epsilon. And so you can estimate the right threshold within an error of epsilon. Okay, so this is how much we need for supervised learning. Instead, you can start with 1 over epsilon unlabeled points. And then you do binary search. You ask for the label of the middle one. If it turns out to be green, then you ask for the label of the 25 percentile point, and so on. And in this way, the number of labels you need is just log 1 over epsilon. And there aren't any hidden constants here either. So it's the improvement is dramatic. It's from 1 over epsilon to log 1 over epsilon. Okay? So this is why we're hopeful. And so the question is, what happens what happens when we take this same reasoning to other hypothesis classes? Okay, so now let's move on to some hypothesis class that is less trivial, a hypothesis class of, say, VC dimension D. Now we know that for supervised learning, we need about D over epsilon labeled points if we want something with error epsilon. Okay, I'm leaving out all the log factors and all that kind of stuff. Okay, so let's follow exactly the same methodology as before. This is the number of label points we need. Let's start with that many unlabeled points. Okay, and now we know again from VC theory that if you have this many unlabeled points, the number of different ways to classify them is D over epsilon to the D. This is Sauer's lemma. Okay. And so this is the effective number of different classifiers that we are choosing between. Okay. Now what we do is suppose we ask queries that cut our version space in half every time. So what we do is we find a query X such that exactly half of the classifiers say it's plus and the other half say it's minus. And we keep doing this. So with each query, once we find out which it is, whether it's plus or minus, our version space gets halved. And in this way, we need only log of this many. Yeah?
Are there guarantees that such queries will exist?
Absolutely not. And we'll get to that in a second. This is a fantasy, okay? But so, so if this worked out, if we were able to do this, this is sort of the dream kind of situation we'd be in, which is, again, this amazing thing where we would get a classifier of error epsilon. Instead of needing 1 over epsilon, we need only log 1 over epsilon points. Yeah?
But when you have a small class of hypotheses, the sample complexity in some sense grows logarithmically with the size of that class. You do like back-learning, right? So you could plug that into the...
No, but this dimension is even better than the cardinality of the set. It's always, the log of the set is always bigger or equal to the VC dimension.
Right.
And it's already using the VC dimension here.
Yeah, so the first problem that Daniel pointed out is that halving queries might not exist. There might not be any point that exactly halves the space. Yeah, Emma. Yeah, so actually, so that's a wonderful, so one example of interaction that I didn't mention is teach-it, where you have a human that is actually choosing maximally informative examples. Okay, so the situation we're talking about is that a machine is given a large amount of unlabeled data and has to figure out which the informative ones are. Well, if there's a teacher who actually knows the concept beforehand, that teacher should be, should be well equipped to actually pick out those informative examples, at least in principle. Okay, that's right. So that could lead to significantly less complexity. Okay, so for example, in the case of the line, instead of needing log 1 over epsilon, you would just need 2 examples. The teacher gives you a negative example just on one side of the threshold and a positive example just on the other side. So with teaching, you just need 2 examples and there'd be no epsilon in there at all. You'd get the grade. Okay. So another issue with this generic framework over here is that, okay, so first of all, it's easy to construct instances where there are no queries that cut the space in half, or even close to it. Every query is highly biased. Almost all the classifiers think it's plus, and there's only a tiny fraction that think it's minus, or vice versa. The other thing is that, in many cases, this D is a large number, and actually juggling a version space of this size is a nightmare. Okay, so it's just, that's intractable. And then also, what do you do when there's 0 error? Okay, this has all been assuming that there's some perfect classifier. Anyway, so there's been a lot of work along this line. And the approach to this is saying, the approach to the first problem, that halving queries might not exist, a natural approach is, okay, you don't have something that exactly halves the space, but just pick whatever comes closest to doing that, okay? Pick the one that most nearly does that, and that's a greedy approach. And many variants of that have been investigated, and especially in cases where the number of effective hypotheses is not that large, this can be super effective. Okay? And another variant is query by committee, which is doing something similar but with a Bayesian prior on top of these hypotheses, and that's also been quite effective. Yeah.
I'll just mention that there, some of the work also addresses that first question of quantifying whether or not these halving queries are going to exist, given the structure of the hypothesis space and the structure of the queries you can make.
Right, right. In understanding what are the situations in which these would, in which these would occur. Yeah. Okay, so I'm going to be talking about 3 types of active learning results. The first, on which there's been a lot of work, which I'll just call mellow active learning. Then a bunch of heuristics that are actually closer to what is typically done in practice, where you sample close to the boundary. And then finally, an approach which I think is very promising in terms of both combining the sort of theoretical analyses and being super practical. Okay? And so let me see whether I get through at least one of these. Okay. So, so mellow active learning, this was a scheme that was introduced in the early 90s by Cohn, Atlas, and Ladner. And so they consider a scenario where this unlabeled data is just coming in one point at a time, and you just have to make these spot decisions. Do I want its label or not? Okay, and then the next point comes in, and you decide, do I want its label or not? And this is a super non-aggressive scheme. Basically, it asks for the labels of everything except the things it is 100% certain about. Okay? So if you're completely sure what the label is, don't ask for it, otherwise ask for it. Okay? So the mellowest possible scheme. So this is assuming that there is a perfect classifier in the class. Okay? So your initial version space is the entire hypothesis class. At each point, you receive a new unlabeled data point. And now if there's any disagreement within your hypothesis, suppose you have 1,000 classifiers left, and 999 of them think this point is plus, and one of them thinks it's minus, there's disagreement, so you ask for the label. If all 1,000 of them think it's plus, then you don't ask for the label. Okay, so those are the only points you don't label. And you keep going in this way. Okay, so for example, let's say you're in this situation. 7 data points have already come in. Now the 8th point has arrived. And you want to decide whether you're going to ask for its label. Well, given the data that you have so far, the candidate hypotheses you have are stuff like this. These are the classifiers that are still in the running. Okay? And all of them think this is a red. So you would not ask for its label. So the only points you would ask for are points that lie in this region of disagreement over here. Okay? These are the only ones you would ask about. And so that's the way this scheme works. Okay? So, so the 2 comments about this. The first is that over here you don't need to explicitly maintain the version space. And the reason for this is you just keep around the label points you've seen so far. When a new point comes around, you say, okay, let me try it with a plus label. So you give it a plus label, you add it to the data set, and then you call your classifier. You say, okay, find me a classifier that's consistent with these points. And you say, okay, let me try with a minus label. You add it to the data set. You say, find me a classifier that's consistent with these labels. So as long as you have something that does this supervised learning for you, you don't actually need to maintain this potentially exponentially large version space. Okay, so it's very efficient. And the second thing is that it basically ends up with a label for everything. So at time t, you have everybody's label. Okay, either you ask for the label, or you filled it in yourself because you were 100% certain what it was. Okay, so nothing goes unlabeled, and say there's no sampling bias at all. Okay, so this is how it takes care of sampling bias. It just makes sure everything's labeled. Okay. Now the amazing thing, or the surprising thing about this scheme is, I mean, you'd think it wouldn't do very much because it's not seeking out informative points. It's just seeking out any point that gives you non-zero information. Okay, and yet you can show that it actually still achieves this kind of log 1 over epsilon dependence on the error rate. Okay? And so this was shown by Steve Haneke. So he characterized the label complexity of this scheme in terms of the VC dimension as usual, but also in terms of this other parameter which he called the disagreement coefficient, and which we'll get to in a few minutes. Okay, but the main thing is that, remember, this was the if I remove this theta, this is sort of the label complexity of the dream scheme, you know, when we could perfectly have. And this achieves the same thing, but with this constant in front, with this constant theta in front. And the dependence on epsilon is just logarithmic instead of the usual 1 over epsilon.
So it's not really a constant because it depends on the marginal distribution.
Right. So it's right. It's not a So it's definitely nothing's a constant, but it doesn't depend on epsilon. So in terms of the dependence on epsilon, you really are getting a log 1 over epsilon dependence, which is surprising for a scheme that's really so mellow. Okay. So let me explain how this comes around. Okay. And by the way, this is only for the case of separable data, but this has been generalized to the non-separable case by various subsets of these people listed here. Okay, so let me explain how this happens. Okay, so why does a simple scheme like this actually get you a very such small label complexity? Okay, so remember that this method essentially gets everybody's label. Okay, either fills it in itself or queries it. So after you've seen t points, you have t labels. You have t labeled points, which means by VC theory that the error rate of any consistent classifier is about d over t. Okay, after you've seen t points, the error rate is d over t. Everything consistent has got an error at most d over t. Now the only points you're going to query are those which have a little bit of, on which there's some disagreement. So let's say the disagreement region of the current version space are those points on which there's some disagreement, and those are the only ones we're going to query. Okay? The disagreement coefficient tells us that this disagreement region is bounded, can be bounded quite easily. Okay? It tells us that the probability mass of this disagreement region is at most the error rate, d over t, times this constant theta, or this not constant theta. Okay. Yeah, Misha.
So you're not worried here how to actually maintain the space?
How to what? No, this is just the analysis. Yeah, we're not maintaining the space. So we'll get to the disagreement coefficient in a second, but this is what it gives us. It bounds the probability of this disagreement region. So now, let's see, the probability of asking a query at time t, you'll only ask a query if the point falls in this disagreement region. And the probability mass of this region, which is the probability of getting a point that you query, is theta times the error rate at that time, which is theta times d over t. And when you sum this over all t, then you get theta times d times log t. Okay? And how far do you need to go? Well, if we want error epsilon, we need to keep going until we have d over epsilon points. So you plug in d over epsilon over here, and therefore you get this bound. Okay? So it's a very simple proof, as long as we manage this deal about the disagreement region. Okay? Okay, so let's look at the disagreement coefficient. So this explains how we get the theta d log d over epsilon. Let's look at the definition of the disagreement coefficient. And this requires us to get a little bit into the geometry of the hypothesis class. Okay, so we have some data space. We have some distribution on that space. And this distribution induces a metric on the hypotheses. So if we look at two classifiers, the distance between them is simply the fraction of data on which they disagree. Okay, very natural pseudo-metric. And this gives us a notion of balls in hypothesis space. You have, say, the target classifier. The ball of radius r around the target classifier is everything that disagrees with it on at most r fraction of data. Okay? So let's look at some examples. Let's say we just have the thresholds along the line. These are two classifiers. Everything to the right is this, and everything to the right is plus, everything to the left is minus. This is another classifier. The distance between them is the probability mass, is the chance that they disagree. So it's the probability mass of this interval. So that's the distance between these two classifiers. The ball of radius r around the target classifier is everything that disagrees with it on less than r fraction of points. So you look at probability mass r to the right, probability mass r to the left, and any threshold that lies in there is in this ball, b of h star comma r. Okay? So this is sort of the geometry of the hypothesis class. Now, the disagreement region is, consists of, so we have our current version space, and we're looking at what are the points on which there's some disagreement. Now, as time goes on, the version space is basically all hypotheses or all classifiers that are consistent with the data you've seen so far. There are lots of different things that this version space could be, but the only ones we need to be bothered with are the ones that are basically balls around the target classifier. Okay? After you've seen d over t points, we're looking at a ball of radius d over t around the target classifier. So we only need to think about version spaces of this form, a ball around the target of radius r. Every other version space we're going to deal with is going to be inside one of these. Okay. And so the disagreement coefficient is the probability of being in that disagreement region divided by the error rate. Okay, and so let's go back to our thresholds. This is the target. The ball of radius r around it is all intervals of probability mass r to the right, a probability mass r to the left. The disagreement region, so we're thinking about classifiers in here. The points on which they disagree are the points that also lie within here. And so this region, the disagreement region, is this red region over here. It has probability mass 2r. And you divide it by r, and so the disagreement coefficient for thresholds is just 2, which means that when you run that procedure on data on the line with thresholds, the label complexity bound is just 2 times log 1 over epsilon. Okay. So now let's look at a slightly more advanced case, which is disagreement for linear separators. So actually, I'm running a little bit short on time, so I think I'm going to just fast forward this part a little bit. Okay, just to say that this was a toy example where we were. So we got a bound for label complexity of any hypothesis class in terms of this disagreement coefficient. And we went through this toy example to obtain its disagreement coefficient. But you can also do this for real concept classes, like linear separators. Okay.
Okay, Sanjoy, I can go a little fast through my section too. So if you want to go through it, I can condense some of mine too. So.
That's okay. I'll move on to the next topic. Okay. So So we have this. So we started with this mellow active learning, which is this very, very simple scheme, queries almost everything, and then somehow manages to get this very low sample complexity, very low label complexity. Okay. Now, I think in practice, however, the behavior of these methods agrees with our intuition that they are just not aggressive enough. Okay. Although the bounds look very impressive, in practice, it turns out that they really are not aggressive enough, and that we need something that is really looking for more informative queries. And so I'm going to talk about 2 different types of work. So there's one kind of work called margin-based active learning. And what this does is that it looks at algorithms that are that for learning linear separators, that are a little closer to sort of the practical heuristics. Okay, so at any given time, you have some estimate of what you think the linear separator is. And the sort of schemes that are used in practice are to query the points that lie very close to that boundary. Okay? So what these schemes do is they say, well, we aren't going to query the points absolutely closest to the boundary, but we're going to look at some margin around it. Okay, we're going to look at some margin, and we're going to query at random from this margin. Okay? And so it's schemes that look like this. Okay? And what is this margin? In the work that's been done so far, this margin is a schedule that is gradually decreasing with time and depends heavily on the underlying distribution. And it's only been analyzed for very special distributions, like the uniform distribution or log concave distributions. Yeah?
When you chose those random points, is that according to the distribution, the underlying distribution? So it's just additional.
Right, but these, right, so it's with respect to the underlying distribution, but the analysis has only been done in the case where this underlying distribution is uniform, or log concave, or
It's not just the analysis, but we know that in other cases it won't work.
Right, so what would be nice is to have a somewhat more adaptive version of this, where where this margin is found in some adaptive way and is not fine-tuned to the distribution. But so let me just quickly give you some of the intuition for this. And the sort of the insight behind these methods is the following. It's if you go back to the supervised learning bound of d over epsilon, you can ask, how many examples do you need to halve the error? Okay? So if you look at this bound, you see that if you want the error to go from 2 epsilon to epsilon, the number of examples you need is something like this. Okay? So the number of examples you need to halve the error depends on what your current error rate is. At the outset, when you're going from error 1 to error 1/2, you need just d examples. Error 1/2 to error 1/4, just d-ish examples, okay? But later on, you start needing more and more examples to halve the error, for the simple reason that most of the examples are useless. They're telling you stuff you already know, okay? So the intuition behind these methods is to always stay in the efficient regime. Never get yourself to the point where you need d over epsilon examples in order to halve the error, okay? And the way you do that is just cut out the regions that you're sure about, okay? When you're getting close to the boundary, cut out the regions you're sure about and operate in a region where your error rate is a constant. And then you'll be in this, and then you can keep halving the error with just d examples.
So you're sampling like that, or how do you do that?
Do you synthesize samples?
No, so the assumption here is that the data distribution is uniform. So, so you'll find plenty of examples in that, right? Okay, so that's the intuition.
Unlabeled examples. There's lots of, okay, so you find those.
Because it's a uniform distribution. So you can get as close as you like to the margin. Okay. Okay, so the last type of active learning that I'll be discussing is what might be called active annotation. And this reformulates the problem a little bit. And let me explain why. Okay, so the problem with a lot of the schemes I've discussed before is that they're really fine-tuned to the type of classifier you're using. So imagine how machine learning is normally done, right? You get this new data set and you're like, okay, I'm going to fit a linear classifier to it. So you use this special active learning algorithm for linear classifiers and it queries a small number of points and you get your linear classifier. But then you say, you know what, this data is not looking very linear to me. I actually need a quadratic classifier. So then you use an active learning scheme for quadratic classifiers. Does it query the same examples? No, completely different examples. You completely wasted the stuff you did before, okay? And then you get the quadratic thing and you're happy with it for 1 or 2 months and then you realize, oh, actually I need a neural network. So then you use the active learning scheme for neural networks, which queries another completely different set of examples, okay? So, so another way to think about the problem, another way to formulate the problem that might be better in general is what might be called active annotation. So you have this data set of endpoints. You don't know anybody's label. The labels are all missing. But you're given some parameters, delta and epsilon. And you have an oracle that can supply any label you want. And now you want to fill in those labels. You're going to query some, you're going to infer the rest, and you want to have this guarantee that almost all the labels are correct. So there's 1 million unlabeled points. You want to query, say, 1,000 of them, fill in the labels of the rest, and have at most epsilon fraction of them be wrong. And then you can use the same data set over and over again with any classifier that you want. Okay, does that make sense? So it's kind of a non-parametric active learning. Okay. And so I'll just describe one scheme of this form, which is a very nice scheme.
Go back to the formulation again. So what are you given and what's the output?
So all you're given is the data set, okay, and maybe some epsilon delta, if you like, okay, and you return a labeling of the data set. Okay, so you query some of the labels. So you have this data set of 100,000, say, unlabeled points. You're going to query some of them, right? And then you fill in the other labels in such a way that at most epsilon fraction of the labels are wrong.
Oh, you know something about the hypothesis class. That's not on the slide.
There are no assumptions about that.
There's no assumptions.
Yeah. So in the worst case, of course, but if while you're looking at the data, it turns out to have nice cluster structure, or it turns out to have some other kind of structure of this form, then that's something that you can potentially exploit. Okay, so this is a non-parametric setting.
Non-parametric, no assumption setting.
Non-parametric, no assumption setting, and the label complexity will depend on whatever structural properties the data actually turns out to have. Okay, so it's like if it's well clustered, then you get low labeling, otherwise not, right? So for example, here is a graph-based formulation where you take your endpoints and you build a neighborhood graph on it. Now everything's got a true label, so let's say the stuff here is plus and the stuff outside is minus. Okay. Then you can think of the complexity of this problem as being the number of edges, the number of cut edges. And that's what you want to find. If you can find the cut edges, then you find the two components, the plus and the minus, okay? And so you want to ask a few queries that helps you identify these cut edges.
So your concepts are connected sets in this graph? Or what is the...
Yeah, so
Drew it as a connected, I'm just trying to...
So the labels can be arbitrary.
So they're not connected, okay.
No, so it could be that, for example, the labels are completely random, in which case the number of cut edges is huge, and you're completely, you're hosed, right? Or it could be that there's some nice structure in there, in which case the number of cut edges is much fewer. And so what you'd like to do is to have a scheme that kind of scales with that number, right? So what would we expect? So let's say you do a little bit of random sampling and you find a point that's a plus and a point that's a minus. So now you know that there's a path that connects them that includes a cut edge. Just by doing binary search along that path, you can find the cut edge. Okay, so you can find each cut edge with log diameter number of queries. And so the total query complexity you would expect to be something like the number of cut edges times log diameter. Something of that form, right? And so let me describe a really nice scheme of this form that's due to Rob and his student Gautam Dasarthi and Jerry Zhu. This is the algorithm. This is the whole thing right here. Okay, so here's what you do, right? At each given step, you say, so initially you have no labels at all, and over time you collect a few labels. At any given point you ask, are there 2 points of opposite label? Do I have 2 points of opposite label? If so, look at all shortest paths connecting points of opposite label, find the shortest such path and query its midpoint. Okay, so for example, we have this graph over here. Initially I have no labels, so I start with a few random queries until I get 2 points of opposite polarity. So now I have this point that's a blue and these 2 points that are white, so I've queried 3 points. Now look for all shortest paths between points of opposite label. So there's one shortest path here and one shortest path here. This is the shorter one, so query its midpoint. And so the next point you query is this one. You query its midpoint. Okay, so now I again have several points of opposite polarity. This is the next point I query, the midpoint. And I've identified one of the cut edges. Okay, and you keep going in this way until you get all the cut edges. So the total time taken is proportional to the number of cut edges times some like log of the kind of path lengths you're dealing with. And those path lengths are in the worst case related to the diameter of the graph, but actually this is done in a way where you're actually trying to keep those path lengths short as well. Yeah.
So this kind of reminds me of Battleship, but you could have some little label up in the left corner randomly, which is a plus, and everything else is a minus. So how do you make sure you actually find that?
Yeah, so the deal, Yeah, so if there are, okay, so let's say, for example, there's just a tiny number of pluses, right? So then, only like 1%. Then you need to sample 100 points in order to get one of those pluses. But also the way in which the active annotation problem is formulated, you're allowed to screw up epsilon fraction of the labels. And so that's also another kind of catch-all.
So basically, yeah, there is this random search element that really can't be overcome if there, you have to. Yeah.
So here the point is that you cannot define, a set of hypotheses and then say that I want to find the best hypothesis.
Yeah, it's just that the different hypotheses, you can imagine a sort of, they're different complexities depending on the number of edges. So it's like sort of a nesting of hypothesis classes. And you want to, okay, so I'm going to move on now so So I'm now going to hand over to Rob, who, as you can see, has been doing some amazing work on active learning, but also more generally on many topics, just in the general area of adaptive signal processing,
Sure.
you say? Okay. Yeah. And so he will continue.
Okay, great. Thanks, Sanjoy. Okay, so Sanjoy did a great job, and Emma did a great job this morning. And actually, what I'm going to talk about, I will try to talk about some other learning problems and structures. What I want to talk about actually is very related to things Emma talked about. And I'll explain why, and I'll get into that a little bit as we go. So I think my mic sounds good. This is the active learning story. And what I really wanted to spend a little time on is talking about how we might go from some of the theory that we've heard to actually working algorithms implemented on real-world problems and trying to close the gap between theory and practice. So one of the motivations for active learning is to reduce the amount of effort required by a human or group of humans helping train a machine to come up with a good predictive model. But I also want to kind of think about this other problem. Sanjoy mentioned it too. Maybe instead of the expense being human effort, the expense is experimental budget. So maybe we're doing some biological experiments, trying to develop a good predictive model based on data coming from those experiments, and we're going to try to use the machine that's learning a model also to guide the selection of experiments to run. And I'll give some examples of both of these as we go. The general idea is that if we just did something random or passive learning, we'd have a certain prediction error as a function of the number of samples or examples. We see the hope with active learning is that we do something adaptive. We let the samples that we collect depend on the past that we've seen, and hopefully that will allow us to learn a good predictive model with fewer samples. The problem is that in a lot of active learning, this adaptivity leads to lots of additional complicating complexity. So not only complexity in the design and analysis of algorithms, but complexity in terms of scalability and computation, complexity in terms of fragility to modeling assumptions and so forth, lots of things we've heard about. And so because of these types of issues, this is one reason why we haven't seen so much active learning fielded and used routinely in practice. So interactivity can help. These are just a kind of laundry list of places where people have tried and developed active learning methods. And the kind of current state of affairs is that promising theory in a lot of these areas hasn't translated into routine practice. So why is that? I've already kind of mentioned computational burden, perhaps of finding and selecting what are those best questions to ask, those best samples to collect. Challenges just of implementation. How do you really do it in the real world when, say, you're working with humans and you have to kind of almost do things in real time? Can you really carry this out? The fragility issues, and then because of some of those fragility issues and so forth, and modeling assumptions, mismodeling, a lot of the theory can end up being overly conservative. We heard that from Sanjoy. Emma mentioned it too. Sometimes the bounds, they're really not all that tight, and while they might give us some insight into how these things are working, they don't really give us kind of practical, usable algorithms. So one of the kind of solutions about how to go about maybe starting to close some of the gaps between theory and practice is to look at specific cases where we have good empirical success, maybe a decent kind of amount of theoretical understanding, and then really try to develop practical algorithms that are robust, scalable, accurate, and work, and give provably kind of guaranteed results. And so I'm going to kind of go back to where Emma started in a lot of her examples. I'm going to think about multi-armed bandits, and I'll say a little bit more about why this is. But basically, I'm going to look at basic multi-armed bandits, linear bandits, and human-machine interaction applications with them. And the reason I decided to focus on that, originally I thought, well, I'll just kind of start to give a laundry list of things people have tried and done. And I felt like I couldn't really go into much detail, and also I couldn't really say much about transferring theory to practice. But here in the context of bandits, I can. And why? Well, the analysis and bounds we have in a lot of these cases are pretty tight. Even the constant factors aren't so bad. So we really have not much of a gap between what happens in theory and what happens in practice. And so that means that we can make algorithms that are basically as aggressive as we can make them in terms of their adaptivity and interactivity while still guaranteeing their performance. So I'm not going to talk about everything under the sun in bandits. I'll just give a couple of examples and go through a little bit of analysis. Emma did a great job of talking about some of that and also about reinforcement learning. Another source for lots of things on bandits is some of Sebastian Bubek's stuff, which I really like. Especially, I was just looking in preparing this over his summer school lectures from last year. These are very good. They're fairly up to date. It was just last May, and so those are really nice sources. And so I'm going to focus mainly on stochastic bandit settings rather than adversarial settings and things like that. So this is the stochastic bandit problem again. The idea is we have some set of arms. We know we have n arms, but each of those arms has an unknown reward distribution. So P1 through Pn, these are unknown to us. And what we're going to do while we play this game is we're going to have to choose an arm at each time step and then draw a random reward from that arm's distribution. And the goal is to select arms that maximize the expected reward. Okay. This leads, as we've heard, to the classic trade-off, explore. We need to learn about these unknown distributions. We start off, we know nothing, so we have to start exploring to learn about those distributions. But after we've explored a little bit, we see that some arms are giving us better rewards on average than others, and we like to exploit that if our goal is to maximize rewards. So here are two examples. One is, I think, familiar to most people here, and that's like displaying ads. So the arms are ads. The actions are which ad to display when a customer comes to a web page, and the reward is whether or not they click. Okay? In a more kind of scientific case, this is a situation where something I've worked with people in Madison on, they have 13,000 strains of fruit flies. Each cell strain is missing a single gene, and they're trying to figure out which genes are important in the process of how a virus replicates in a host organism. So each of these strains of cells is an arm. They can infect a culture of a particular strain with a virus and then measure how much that virus is able to replicate itself. And that virus replication level is sort of the reward we get on that experiment. And so what they'd like to do, there are 13,000 strains. They have to grow a little culture of each strain. They have to infect it. They have to wait a while. It's expensive, time-consuming. They'd like to figure out which genes are most important in virus replication with the fewest number of experiments. And you can also formulate this as a bandit. Arms are genes, actions are which gene strains to infect in a new experiment, and then the reward is what they observe in terms of virus replication. Okay? So the way you can start thinking about this, and Emma discussed it a bit, is we have arms. For each arm, the blue dots are our empirical average reward that we've observed. And then we also have a confidence interval around that average. That confidence interval, basically we're saying with large probability, the true mean lies within that interval. And those intervals are basically proportional to 1 over the square root of the number of samples you've taken from that particular arm. Okay. So the more samples we get, the smaller the intervals become. And you can see that if you thought, for example, of like the version space idea that Sanjoy was mentioning, if I see that, well, I'm pretty confident, based on this confidence interval, that the mean of this arm is somewhere in this range, the true mean. But some of these other arms, we're very confident that they can't possibly be as high as that lower bound. So we could discard those guys, trim our version space, if you will. And this is one type of bandit algorithm. It's called successive reject or successive elimination. Okay. Let me just give a little bit of notation. So arms, we have n of them. each arm has an expected reward, mu1 through mu(n). I'll just assume for convenience that mu1 is the largest, so that would be the arm that has the highest expected reward. An important parameter are the gaps. Emma mentioned it very briefly, but I'll just kind of define it here. The gap, delta I, is the gap between the largest expected reward and the reward we get from some other arm, mu sub I. So sort of the gap in the reward between the best one and some suboptimal arm. XIT are random rewards that we obtain from arm I at time t. And then mu hat IT sub I is just the empirical mean of arm I after we've collected TI random rewards from it. And so one of the things, again, was mentioned briefly, you could assume that your rewards are bounded or that they're sub-Gaussian. Then what that means is that your empirical mean starts to look kind of like a Gaussian distribution around the true mean, and that it's concentrating very quickly about that true mean. If I've taken t samples, then this is concentrating exponentially quickly with t. Okay. And you can generalize this. It doesn't have to be bounded or sub-Gaussian. It could be sub-exponential or other types of tail kinds of bounds on what you think the rewards distributions look like. But if you have that, then what you can do is you can get confidence intervals. So here's my true mean, the empirical mean, and I'm sort of putting those confidence intervals around that true mean. And the width of that confidence interval is basically proportional to log t over t and the square root of that. And I'll use those kinds of confidence intervals as we go. OK, so two problems we could look at. One is, well, I'll call like a prediction problem. This is just where we're trying to minimize our regret. That's just, again, the difference between the reward we could get if we played the expected reward we get if we always played the best arm. And then we're comparing that to the expected rewards we get based on what we actually do play. So that's our regret. And if you kind of just think about this a little bit, you can rewrite it quickly and see where these gaps start to play a role. You can express this regret as a sum over all the arms, the gap of each arm from the best arm, and then the expected number of times you've actually sampled that suboptimal arm. Okay? So the gaps show up right there. And what this is saying is we want to maximize the clicks in this web advertising problem, or we want to maximize the total virus replication that we see in our experiments. So maybe if you were doing something else and you're trying to maybe get organisms to produce something like a fuel or something, maybe this would be a great model for that. You'd like to maximize through experimentation how much fuel or whatever you can do have those organisms produce.
Actually, aren't you minimizing the number of misclicks and minimizing sort of missed replication by using regret?
So we're just trying. So what you're trying to do is select the arm that makes it most probable that somebody's going to click on it. So maximizing the probability that somebody will click is the same as minimizing this regret. The other problem that you could think about in this context is more of a model selection problem, where you're not just trying to maximize your rewards, but you're actually trying to identify which arm is that arm with giving you the largest reward. And so here you'd like to do something more like pure exploration, maybe choose a sequence of arms in order to just kind of identify as quickly as possible which arm is the best average reward. So identify the arm that maximizes expected clicks or that maximizes virus replication, which would be, in that virus replication example, identifying the gene that is most important in the virus replication process. OK, so why, again, let me come back to the issue of why I'm talking again about bandits. So the important thing is that near optimal algorithms exist for these problems. And not only are they order optimal, but the constants are actually pretty good. So we have a very, very small gap between what we understand theoretically and what we actually observe empirically and through simulation. So this is an algorithm. Again, Emma mentioned it, an upper confidence bound algorithm that's based on this sort of heuristic of optimism in the face of uncertainty. So the idea is that here I'm showing you the arms And at each step of this process, you're going to sample the arm that has the largest upper confidence bound. And if you do that, what happens is it basically tends to equalize all these upper confidence bounds. And in doing that, you end up really focusing on arms with higher means and shrinking those confidence intervals much more than others. Down here, I'm just plotting the number of times each arm has been sampled. And you can see just by virtue of this process, and maybe I can run it again, what happens is you start off initially sampling more or less at random, but quickly over time, you start focusing on arms with higher payoffs. And it turns out that strategy is basically managing both exploration and exploitation in a really nice way. Okay, so let me go back to this. So one of the things that you could kind of convince yourself of, if you think about this a little bit, is eventually this kind of algorithm is going to stop sampling suboptimal arms as long as there's some gap between the highest mean and the second highest mean. What's going to happen is eventually you can't shrink this guy as long as these are all valid confidence intervals. Once this guy gets shrunk far enough, he's separating from all the others, and you'll stop sampling all the others. Yeah?
Is this changing if the distributions of the single arms are changing as well? So for example, if n is now the best one, does this change?
Could you just repeat that? I'm sorry.
If the distributions of the single arms are changing.
If the distributions are changing over time.
Yes, is this
So here I'm assuming that the distributions are fixed and you're getting independent and identically distributed samples every time you sample from a given arm. So those distributions are not varying over time in this setup. Yes?
This does mean that there's some probability that the optimal arm only gets sampled finitely many times?
Yeah, so when I say eventually we'll stop sampling, that's with large probability that you specify ahead of time. So say you want to say, I want to be 99% confident that nothing goes wrong in this procedure. These would all be kind of under the caveat of with some large probability that you decide on ahead of time, for example.
Literally just sampling the one with the largest upper bound.
Yep.
How do you parameterize that algorithm?
Well, maybe that'll become clear in a slide or two, if you just give me a second. And if not, then let's come back to that. So what can you say about this UCB-style algorithm? Basically, you say that in terms of regret, the regret basically behaves at time capital T after capital T samples. The regret something like sum of the inverse gaps, some of those delta i's, 1 over them, times log T. And in terms of selecting the best arm, and I'll go through this a little bit to explain where it comes from in a minute, you can find the top arm in capital T samples where capital T grows roughly like the sum of the inverse gaps squared times a log-log factor. And I'll explain that in a minute. But both of these upper bounds are essentially tight. And even the constants are small, as I said. So there's not a huge amount of wiggle room, unlike some of the other problems that we'd love to solve that I think are great open challenges, how to make things like high-dimensional linear classifiers work actively and provably good. That's something I don't feel like we're there yet. OK, so let me just kind of quickly explain. Maybe this will help clarify things a little bit for Daniel. So the idea is that here are my confidence intervals. And they're basically of the form, again, something like log T over T in the square root. So that's the width of the confidence interval. And this delta, this is my confidence that all of these things are holding true. Okay, so you can choose that as you like in this setup. So you take delta to be 1%. So there's a 1% chance that things fail. This is our upper confidence bound for arm I. It's the empirical mean plus that half width of the confidence interval. And here's the simple idea to get a little bit of sense of why these algorithms work. So we're going to, the algorithm samples the arm with the largest upper confidence bound. So arm I is sampled only if its upper confidence bound, which is this, is greater than the corresponding upper confidence bound of arm 1, which is the one that we are assuming in this analysis to have the largest true mean. Okay? So the picture looks like this. This guy's upper confidence bound is a little higher, so we're going to sample him instead of that one. Now, if we assume that these confidence intervals are valid, and that arm I was sampled, say, capital TI times so far, what we know is that the upper confidence bound for 1 has to be larger than its mean, and the upper confidence bound for arm I has to be less than its mean plus the full width of that confidence interval. So what I'm saying here is just, I'm saying like in kind of a worst case situation, this guy's mean is right up hitting at the border there, and this guy's mean is way down here. But we know both of them have to be, if these are valid, the true means have to be in those intervals, and so we could have this kind of inequality going. And if we then just arrange that inequality and move the mu I over to the other side, what it tells us is the gap, delta I, has to be less than or equal to the full width of the confidence interval for arm I. Okay?
Shouldn't UCB1 just be greater than mu1 minus its lower bound? Why isn't the minus?
This guy?
Yeah.
I'm just saying that he could be anywhere, so I'll put him right at the top of his, right? So this mu1 is somewhere in this interval. So the biggest he could be is right at the top. Mu I is somewhere in this interval. So the smallest he could be is right at the bottom. And that's all I'm saying. And then I'm saying, if we're in the situation where we're going to sample arm I, it must be that this upper confidence bound exceeds this one, and that gives us this inequality. And so where, I should say, where this comes from a little bit is kind of the law of the iterated logarithm. If you're wondering where that log comes from, it has to be there. It's not just an artifact of some looseness in analysis. And if you invert that, then you basically get this kind of bound on the number of times you'll ever sample a suboptimal arm I. It's going to be on the order of 1 over the inverse gap, or the inverse gap squared, and then log of that inverse gap squared. Okay? So this is basically saying, like, if we just follow this simple strategy, with large probability, we're going to eventually stop sampling suboptimal arms, and so we're going to home in on the top. Yeah?
So the logs are to make sure that with 1 minus delta probability, the confidence interval is all of the confidence intervals.
So right now, I'm just sort of thinking of, so no, if we did really want to have them all be truly simultaneously valid, we'd have to have an extra n in here for a union bound over all those. Yeah. Sorry?
All the confidence intervals for the ith.
Yeah, this is just for the ith guy alone in isolation. It would look something like this. And this log is there because you don't know, essentially it's there because you don't know how big that gap is. And so you really have to suffer that extra log factor because of that unknown width of the gap delta. Okay, so that, I hope, is simple enough and convinces you that this simple algorithm should work well. What it basically tells us is that the UCB algorithm, the total number of times we sample suboptimal arms grows like sum of the inverse gap squared. And just to kind of do something silly, not that I'd recommend this, but you could say, well, let's, instead of doing anything active, or wait, Jake, you had a question.
Go back one slide, sorry to interrupt.
Yeah.
But the log part, I mean, you can just use Hoeffding's inequality to get just log t over delta, right? You're just, this is a tighter, slightly tighter bound. I mean, you could have replaced that with just log t over
Sure.
delta.
Yep.
And that is true. That still holds the.
Still holds. This is, if you might wonder if I even need anything up here, right? If I could just have log 1 over delta or something. But you do need something there, and that you do need, so yeah, this is sharper up in terms of the order dependence on t.
How do you justify not taking into account the need for union bound over all other arms?
So that's a great question, and I'm not going to get into it, but basically this algorithm that we use, and I'll show you it in action in a minute, we don't try to actually have control over all the arm's confidence intervals. What we do is we try to control just 2 variables, the confidence interval for the top arm, and then we try to control a random variable which is equal to the total sum of the number of times you play suboptimal arms, and then we have a random stopping time based on the number of times you've pulled arms. So we kind of forego, in at least the nicest theory, we don't need to union bound over all the arms. And if you want, we can chat about that afterwards. Yeah.
Give me an intuition. If I would just take the highest mean, it would work, right? I need to get confidence into
If you just took the highest mean, it wouldn't work. You need to take the confidence interval.
Yeah, why?
Why? I'm not sure if I have a quick answer for that off the top of my head. Maybe somebody else does, or
yeah, because there's a bad probability event that the guy that is the top arm accidentally looks a lot lower and then stays there forever. So what you sampled for him is below the interval for anybody else, and they just stay within their interval forever.
something like that could happen. I mean, there are other strategies, so I don't want to say this is the only strategy you could use. The other one is a successive elimination or something. But yeah, this one works well in practice. Yeah, thanks. It's not my idea, but we did some extra analysis to try to tighten up the bounds as much as we could and get things to work in practice.
So what is the probability that you end up with the wrong one?
The probability that you would end up with the wrong one in this kind of situation when you go, if your goal is to find the arm that has the highest empirical mean, the failure probability would be this value delta, which you choose ahead of time. Or proportional to delta.
Won't it get large if you have a million, bajillion different arms? What is delta per arm?
No. Well, let's talk about it afterwards. So quickly, well, I was just about to say, what if we just did something naive, like sample non-adaptively, which means essentially sample every arm equally often. We could do that, and eventually we'll also shrink these confidence intervals and be able to figure out which one's best. But if you think about how many times you're going to need to sample there, you have to sample every arm essentially as many times as you have to sample the second best to separate it from the best, which is 1 over the smallest gap squared. And so the total number of samples for a non-adaptive procedure would be n, the number of arms, times the inverse of the smallest gap squared. And so if the smallest gap is small and all the others are large, you might be as much as a factor of n off of what you could do with the Bandit. Okay, so one of the things we wanted to do, and I don't know how much time I'll have, but I'll just say this. This is a long-running experiment that we've done to actually test out how do these algorithms work in practice. We've used this experimental collaboration also to evaluate and prove algorithms, both in theory and in practice. And this is something we're doing with Bob Mankoff, the cartoon editor from The New Yorker. So the basic idea is that every week 5,000 captions are submitted. So there's a cartoon published without a caption, and readers are invited to try to submit a funny caption. They get about 5,000 entries to this contest every week. We then crowdsource the rating of these submissions to a set of volunteers who provide us ratings for captions, and the goal is to identify which one's funniest, to choose a winner in this contest. And we've got over a year now of experiments, and each week we're running these Bandit algorithms with real humans to see how they work. This is what it looks like in the New Yorker page. I don't know if I'm on the internet here. I guess I am. Maybe I shouldn't have done this, but here it is. This is this week's caption contest. And basically the idea is when you come to the system, you're using a 3-star rating process. Do you think this is unfunny, somewhat funny, and funny? The user or volunteer then clicks what they think. And now this Bandit selects another caption that was submitted adaptively and tries to collect a rating. Okay. Let me close that and see if I can get back to this talk quickly. Maybe I shouldn't have done that. Uh-oh. What did I do? Well, that's your out. Did I close mine? Oh, there you are. Sorry. OK. So this is what it looks like. This is one actual contest where there was about 4,000, a little more than 4,000 submissions. These are the total number of times each caption has been rated. You can see that initially the ratings are more or less uniformly random, but over time we start focusing on those that are receiving higher ratings. These are the average ratings that we're receiving. And there's a very little gap between theory and practice in this problem. It's working very well. I'll just quickly flash up some analysis we've done where we've actually taken a large number of ratings, figured out what is the funniest caption, and then repeated the Bandit algorithms and then just a conventional crowdsourcing, which is non-adaptive. And we see that we get about a 5x improvement in terms of how many samples we need to get a pretty good sense of what are the top captions. So that's pretty significant. quickly, I'll just say a little bit about structured bandits. So this is kind of taking it a little bit further. We started off with the very simplest interactive learning problem. Now we get a little more complicated. There are a lot of varieties of structured bandits. We've heard a little bit about some of them: linear bandits, combinatorial bandits, Lipschitz bandits, contextual bandits. I'm just going to say a little bit about linear bandits, because they have nice applications, and they have a nice theory that also kind of just follows along from what we've been talking about. I'll quickly go through that. So the idea is we have arms now of our bandit, but each arm is associated with some added side information in the form of a feature vector. Okay? So our arms are vectors in RD. We have a reward vector theta star, and the rewards that we actually receive are going to be inner products between the feature vector for the arm that we select and this weighting given by theta star, plus a little noise. So y is our reward. So features that are more well aligned with this theta star get higher rewards on average. The optimal arm would be the one that gives you the largest expected reward. That's just this, and I'm showing him here. And the regret we're going to look at is the difference between the expected reward we get if we played this optimal arm all the time versus the expected value of the rewards we receive by playing the arms we select along the way. The one way to tackle these problems is with the same idea, this optimism in the face of uncertainty. In this setting, what we're going to do is try to construct a confidence set, CT, so that at every time t, theta star belongs to that confidence set. And this is done in a number of papers. The kind of approach I'm going to talk about here, the bound I'm going to give, is from the last paper, that 2011 there. So the basic idea to kind of figure out what this confidence set is you just form essentially the least squares or ridge regression estimate of theta given the data that you've collected so far. So you've chosen some arms, you know what those are, you see the rewards, you use those arms and rewards to construct an estimate of what you think theta looks like. That's called theta hat. And if lambda is small here, this little regularization parameter, if it's a small value, then basically this first part is about theta star, and the rest is this stochastic term here. And you can kind of just rearrange that, so now theta star is like theta hat plus a little error. And using some martingale concentration techniques and so forth, what you can do is you can get a confidence ellipsoid. That's that set that I'm showing there in gray. It's basically a weighted inner product of the distance from theta hat, and then you have a width that depends on the dimension of the problem, d, the number of time steps you've taken, t, and a little bit on the regularization parameter, and then again you see your confidence parameter, delta. So the optimism in the face of uncertainty is the same idea again. We're going to say, okay, well, let's find an upper confidence bound for each arm. How do we do that? Well, we take each arm, say the ith arm, and we say, what is the best possible expected reward I could hope to get if I know that I'm somewhere in here? So you maximize over theta. That gives you an upper bound on what the expected reward could be for arm I. And then at each time step, you just sample the arm with the highest upper confidence bound. This is the algorithm. So this is the double maximization that you perform each time to choose which arm, to decide which arm to sample. It turns out that you can simplify that inner optimization over theta, because this is just an ellipsoidal set. That ends up looking like this. And if you inspect this, then you see exactly two terms. One that's the exploit term, try to choose an arm that matches where you think theta is. And then this term, which is basically looking at something like the sample covariance here and saying, explore in directions you haven't looked so much so far. Okay? And you have regret bounds that are problem independent. You have problem dependent ones that involve something like a gap again. And these are also near optimal in terms of the order of dependence on dimension and time and so forth. So let me just kind of give a quick example. So I basically spent a little time looking around what are the best algorithms for linear bandits. These are among those, and then we try to see how well they work in a real problem. So this is sort of an interactive image search problem. So the traditional image search problem would be the user gives an initial target image, that goes to the system and the database, and the machine tries to retrieve similar examples. The interactive version of this is that the machine retrieves examples, but after each example, the person indicates whether or not it was really matching what they like. So maybe they weren't just interested in tall boots, but they really wanted red boots. Or maybe red wasn't so important. In another case, it was some other feature that they were attending to and focusing on. So this kind of feedback allows the system to potentially improve the retrievals in this image search. So this is a data set people use for this sort of thing. This is the Zappos data set, 50,000 shoe images, large variety of styles. We featurized each of them using deep learning features, so we end up with about a 1,000-dimensional feature vector for each shoe. Those are our X's in our linear bandit. Then we had human subjects. We sort of primed them. We said, you want to pick out red boots. We start this system off. They can say, is this a good match to a red boot or not? We tried different targets, different experiments of this form. One of the challenges is that when a person is doing this, this has to be happening basically in real time. And even one pass of that algorithm requires a search over the whole database. So that's 50,000 images in this case. So it's non-trivial even to implement these algorithms in real time. And so we have a bunch of approximation algorithms for this with some theoretical guarantees. But again, now, will they really work in practice? Or when you go through all that stuff, do you get something that doesn't work any better than something simple like a nearest neighbor non-adaptive thing? So we wanted to test this. And so here are some results. They're kind of typical of what we saw. The green baseline here is just nearest neighbor retrievals. The colored curves above are all of the different varieties of bandit approximations that we developed. And what you can kind of see from this is that the linear bandits are retrieving 2 to 3 times as many relevant items as just the non-adaptive approach. So there's working reasonably well in practice, working well enough to make it worth doing something like this. Because there's a lot of overhead in getting this going. And in the last 2 minutes, that's what I want to talk about. What is the overhead involved and how do you do it? And this is one of the barriers I think that's been there between transferring theory to practice, is that it's just very, very difficult to even do an experiment like that. So there are a lot of practical challenges. I've already mentioned them. Data management issues, real-time computing issues. Why is that a problem? Well, researchers aren't able to easily field and test interactive learning algorithms. Theoreticians might not really be working on the right problems because we don't know really what's going to come up in practice. So there could be really cool challenges that come up when you start to try to do these things in the real world that have interesting mathematical solutions. And then just routine practitioners who aren't necessarily algorithm developers or theory provers can't even use these things because there's no infrastructure to support it. So people have tried to change that problem. And one effort is Microsoft's multi-world testing decision service. Another is something we started at Madison called Next. I don't know, maybe I won't say too much about these, but I will put in a little plug because it's tea time. And what I hope to do during the interactive workshop, which is in a few weeks in February, is have Alec Agrawal, who has been really involved in Microsoft's effort, and Kevin Jameson and Lalit Jain, who are both here, who are 2 students who really spearheaded the project at Madison. Maybe we'll carve out an hour or something where we can hear from both of those groups a little bit about how these systems can be used, how they can facilitate real-world experimentation with active learning algorithms. And I think I'll just stop there.
There was very little discussion about the noise.
The noise.
Yeah, so whenever, you have these active learning algorithms, well, when the response is noisy, what do you do?
Yeah, so of course, in these bandits, we're accounting for the noise. For example, in the cartoon caption rating contest, we know that the ratings are either 0, 1, 2, say, where you have a 2, 3-star scale or whatever. And so we know something about what the largest variability could be in the empirical process of collecting ratings for a given caption. We use that information then to construct these confidence intervals. We were just using the fact that basically they were sub-Gaussian and kind of like a Hufting type bound was the starting point, but you can do a little bit better than that using things like KL-derived, Kullback-Leibler divergence type bounds, and you get even better performance. But yeah, so we kind of try to make minimal assumptions about the noise. If we know things are bounded, that's one starting point. We can put some sort of limits on how noisy things could be, if you will.
So the thing was basically you ask the user,
Yeah.
the user might not fit.
Yeah, so
That is a noise.
yeah, so imagine we have one cartoon caption that we wanted to get ratings from. We all won't agree. Some people think it's funny, some people think it's not. But if we imagine that the ground truth rating was what we all said, but now I just ask a random subsample of 10, now I have an empirical estimate of that ground truth mean, that's the ensemble mean that comes from all of us rating it. And so, so I mean, that is where the noise is coming from, just variability in people's responses, and that's what we're trying to account for. Does that help?
Yeah, that helps, but it's more than that, I think.
Well, maybe we can chat more at the break. Okay, well, thank you.